Guess we need to go ahead and get started. I just let another person in. Again, go ahead and chat me your first and last name if you haven't done so already. I'll try to remind y'all later. We are starting into chapter 21, and largely I like to leave the conceptual aspects to you guys. Actually, I like to do a lot of demonstrations, but we normally don't have enough time. So, what I do is I have various videos I posted in the helpful documents and links areas where it shows you some demonstrations uh, with actual equipment and working with electrostatics and stuff of that sort. But I do need you guys to understand some of the basics of electricity and magnetism. So, the word electricity came from electron, which was the Greek word for amber, and basically amber is petrified tree resin. And what they discovered, even in the times of ancient Greece, they had discovered that if you rub fur or something like that against a piece of amber, that then the piece of amber could pick up little random things uh, of very specific materials and stuff like that, but they didn't necessarily put all that together and figure out what was what. All they knew is that when they rubbed amber, that both the thing they rubbed the amber with as well as the amber itself could, in principle, pick up stuff. Later on, it was worked out that basically there were two different flavors, if you will, of this electricity, and which actually we now call a charge, one of which was positive and one of which we called negative. That was all by Ben Franklin's doings. He was the one that chose to use the positive and negative as the indicators of the two different types of quote unquote electricity. We now call that buildup, like when you take a piece of amber and rub it with fur, and then the amber is attractive to like pieces of paper or something like that. We call that static electricity. And we know at the microscopic level what's going on is when we rub two materials together, in principle, one material has a stronger urge to steal electrons or hold on to its electrons than the other material does. Therefore, the material that wins, i.e., the one that has the largest affinity for electrons, ultimately steals electrons from the other one. In the case of amber, it turns out that amber and plastic generally steals electrons from other things, so they become negatively charged. However, if you take glass and rub fur on that, that'll actually generate a positive charge. In other words, the fur has more affinity for the electrons than does the glass, so that the glass becomes positively charged. What we also discovered, of course, is like charges repel. So if you take two pieces of glass that have been charged the same way, you bring them near each other, they'll repel. Even without touching, you can still feel a force of repulsion between them. And similarly, if you brought two pieces of amber together that had been rubbed, they would repel each other. But the other aspect is that when you bring a piece of the amber, which was negatively charged, and the glass, which was positively charged, if you brought those two together, they'd be attractive. So, like charges repel, unlike charges attract. And not only that, it was stated by Ben Franklin that basically it seemed to him that when you actually did rub cloth on a piece of amber, say, the amber would accumulate a certain amount of charge and the cloth would accumulate a certain amount of charge, but they would be exactly opposite, so that we hypothesized what's now called the conservation of charge. So we do know that charge is neither created nor destroyed, and we've never, ever, ever found a contradiction to that. So when we're talking at that microscopic level, when we say amber, for instance, become negatively charged, we know that what's happened is negative charges that made the atoms neutral in the cloth or the fur or whatever you were using. The amber actually stole those electrons from those neutral atoms, and for each electron that the amber stole, that made the amber a charge of -1 for the electron, but it also made the cloth a charge of +1, so that -1 and +1 gives you 0. Now, your book talks about charging by induction, charging by polarization, all that good stuff. It talks about insulators and conductors and semiconductors. All of those bold-faced terms in chapter 21, you need to go ahead and read and make sure you make some sense of. Uh, Mainly so you can have some understanding of the concepts and therefore do well on the conceptual homework as well as the conceptual test questions that will appear later. So make sure you follow that. I will let you know that, for instance, during the winter when you scuff your feet on the carpet and then you go to grab a doorknob and it actually shocks you, if you were attentive enough, you'd actually see a little blue flame either jumping from your hand to the doorknob or from the doorknob to your hand, and it's not necessarily obvious which one it is doing. I'm just saying it appears there between the two, and you don't know which way it's coming or going. But if you see that, then that is essentially a lightning strike, and that's essentially what happens in storms, specifically in the clouds, ice particles and particles of water and stuff of that sort hit against each other, and they actually cause a buildup of charge as well. So each time an ice particle bumps in with another ice particle or a bit of cloud material, that sort of thing, they can actually strip electrons off of those individual atoms until eventually you get so many charges build up that it's a huge, what we call voltage difference between one spot of the cloud and another spot, or between one spot in the cloud and the ground, or one spot in the cloud and another spot in the same cloud. So that makes intra-cloud lightning, so that's lightning within one cloud. It makes cloud to cloud lightning, which goes from one cloud to another, or it makes cloud to ground slash ground to cloud lightning as well. And what's going on there is if the voltage and therefore the electric field that's creating that voltage, if that electric field gets large enough, then the air in the atmosphere, which is generally a really good insulator, becomes a conductor. And when that happens, it allows electricity to flow, but it does so in a step-like pattern because it's got to go basically to the nearest free charge, then to the nearest free charge, and the nearest free charge, and nearest free charge. So it doesn't necessarily have a plan of where it's going. It just sort of jumps from the next closest piece to the next closest piece. So that's a quick abbreviated version of how lightning works. I will mention that insulators generally hold on tight to their electrons, and conductors generally hold on less tight to their electrons. So that what makes the difference between something you would call a insulator versus something you'd call a conductor would be that when you have a chunk of atoms connected together that are all atoms of a conductor, let's say a metal, then the electrons sort of break loose from their mother atoms and they just sort of wander around the whole metal material or the whole conductive material. Whereas if you take like ceramic or glass or porcelain or something like that, that is an insulator, and if you looked at the microscopic level there, you'd find that the atoms are holding strongly to their electrons, so the electrons aren't free to move. But as I pointed out in the lightning story, air, which is an insulator, if you subject it to a big enough electric field, it too becomes a conductor. So I want you to remember that there's not insulators and conductors. There's a continuous spectrum between insulator and conductor, and what one group might consider an insulator, another group might consider a conductor, just because the other group might work in a higher voltage range or a higher electric field strength range. So I do recommend you going on YouTube, looking for as many electricity demonstrations as you can, as well as look at the ones in uh, my important documents and links module within Canvas. So check those out. What I'm going to do now is I'm going to go ahead into the part where I'm going to do the calculational stuff so that y'all can know how to do that. The chapter is 21. It's called Electric Charge and Electric Field. We're first going to introduce the force equation for charges. So as I told you, like charges repel and unlike charges attract. But there's a formula that tells you how they attract, and the formula looks surprisingly like the formula for gravity. And that's partly because that was their first guess, and it just turned out to work really well. Okay. So what it's called is Coulomb's law. I'm going to go ahead and share my computer screen with you, or my iPad screen with you, and I'm going to write down Coulomb's law and give you some specific important constants, and then I'm going to show you how to work with it. Specifically, the big part about PHY 242 is that this is where you start doing vector calculus. There's a lot of vector calculus in here, and you're starting to learn how to do it already. So that's a big part. And part of that it entails you being able to actually take a formula for a magnitude of a vector and then convert it into an actual vector. So I need to make sure you guys can do that. Later on, I'll even show you things like gradients and partial derivatives and curls and uh, divergence and all sorts of good stuff. So again, what we know is charge is conserved, and we know like charges repel, and unlike charges attract. Okay, and let's see what else. Insulators hold onto their electrons with a lot of force. Conductors have a loose hold on at least one of their electrons. Okay. Now notice everything I'm talking about here is electrons. That's the way, and you've hopefully already learned this from chemistry or even high school, basic physical science and earth science. But when things become charged, generally they become charged because they've gained an electron or they lost an electron. So an electron has a negative charge, and they basically are lost in increments of whole electrons are gained in terms of whole electrons. I should also point out that the electron charge is negative E, and that is negative 1.602 times 10 to the negative 19th coulombs. So I'm getting ready to show you Coulomb's law, and of course the Coulomb's law was named after a scientist with the last name Coulomb, and that's also what the unit of charge is named after. So this Coulomb that I'm showing you here is a fundamental SI unit for charge. You can look at it as part of current, or you could say Coulomb is the fundamental charge. I think the latest definition actually has them treating the ampere as the fundamental quantity and then the Coulomb as the amp second. So that might be the case. Just you can look over your reading as you're doing that. But the main thing is you need to know that the charge of an electron is negative 1.602 times 10 to the negative 19th, and the charge of a proton. So this one is an electron. Okay. And then E is the charge of a proton, and that is positive 1.602 times 10 to the negative 19th coulombs. And that's the charge for a proton. Now, the neutron, of course, has no charge, but this is the fundamental unit of charge. Now, if you've learned a little bit about physics beyond classical physics, then you probably heard of quarks and things like that. And generally speaking, quarks can be like a third or a half of an electron charge, but they're not stable particles. If you find one of those, it's going to disappear really, really quickly because it's going to decay into something else or combine with something else. Whereas an electron is a stable particle that can exist by itself. A proton is a stable particle that exists by itself. The electron, as best we can tell, is a fundamental particle. We don't believe it's made up of anything, and in fact, fact, we don't even believe it has a physical size. So far, we've narrowed it down to, I think, 10 to the negative 19 maybe meters. So it's definitely smaller than 10 to the negative 19th meters, which is, 10 to the negative 14 is basically about the size of the nucleus. So the electron is at least 100,000 times smaller than that. The proton, on the other hand, has a physical dimension, and it is made up of quarks, as is the neutron, and so on and so forth. So, the law of gravity, you'll recall, was Newton's law of gravity, and it said that F is equal to G m1 m2 over r squared, where r was the distance between mass m1 and m2. And what you see here is that the force and the mass m1 are thumbs up, thumbs up. Notice F is on the left side of the equal symbol and M1 is on the right side of the equal symbol, but they're both in the numerator. Again, there's no numerator or denominator on the left-hand side, so that means to make it a fraction, you would write the F over 1, in which case you realize the F is in the numerator, just like the M1. So F and M1 are thumbs up, thumbs up. That means if I double M1, I double the force. If I double or if I increase M1 from 1 to 1.78, then I'm going to increase the force to a multiple of 1.78 times what the force was before. Similarly, M2 and F are thumbs up, thumbs up. So if I double M1 and I double M2, or let's say if I double M1 and I triple M2, then I'm going to increase the force by a factor of 2 times 3 equals 6. And then finally, you'll see that F and R are thumbs up, thumbs down, and that's because the F is in the numerator and on the left-hand side of the equals. The R is on the right-hand side of the equals, which is what we need, but it's in the denominator, and that's the difference. Numerator and numerator on opposite sides, are denominator and denominator on opposite side. They're thumbs up, thumbs up. But if they're opposite sides of the equal and opposite sides of the fraction bar, then they're thumbs up, thumbs down. Okay, so that was Newton's law of gravity, and I'll just remind you that in that scenario, G was the gravitational constant of the universe, and that was 6.67 times 10 to the negative 11th, and that was measured in Newton meters squared per kilogram squared. Now, Coulomb's law is very similar to this. And that force is given by F is equal to, and there's a couple different ways to write it. I hardly ever write it with this K because I hate this K. And the more robust equations of Maxwell don't use K, so that's why we'll ultimately get rid of it. But it's very convenient to use sometime. So F is equal to K Q1 Q2 over r squared, where Q1 and Q2 are the charges. Okay, so Q1 is a charge of particle 1, and Q2 is a charge of particle 2. And both of these equations are essentially thought of as being used to deal with point charges, but we could actually imagine that all matter is made up of molecules or atoms, and they're so much smaller than the macroscopic world that we can pretend like they're infinitesimally small, and then we could actually integrate things to get the total force due to a mass distribution as opposed to individual particles. But these formulas are basically written for individual particles, or as Newton showed us with his law of gravity, that if the mass is spherically oriented, in other words, you've got basically a mass m1 that is spherically symmetric, so that it acts as if all of its mass is at the center, then you can actually use a sphere just like it is a point particle as well. You just can't mess with the area within the point particle because that's not really a space that's supposed to exist. So long as you stay outside of the geometric confines of the individual non-particle, the actual sphere, then the equations that you get by treating it as a point particle are just fine. And by the symmetry of that, Newton's law of gravity and Coulomb's law of electrostatics, you can see that clearly whatever arguments Newton made to make that conclusion about spherical distributions of mass, we can make the exact same argument about spherical distributions of charge. So again, we see here F and Q1 thumbs up, F and Q2 thumbs up, and F and R is thumbs up, thumbs down. But F and R being thumbs down, just like gravity, has that exponent of 2. It's a 1 over R squared law. So that means if you increase the distance between the two particles by a factor of 2, you decrease the force, but not by a factor of 2, but by a factor of 2 squared, which is 4. Similarly, if you triple the distance between them, then you decrease the force by a factor of 3 squared, which is 9. If you quadruple it, it's going to decrease it by a factor of 16. If you quintuple it, it's going to reduce by a factor of 25, so on and so forth. Now, here's the big difference between, well, one of the many big differences between the gravitational force and the Coulomb force. The constant in the Coulomb force, K, is equal to 8.988 times 10 to the ninth. So it's a billion. Remember, this one for gravity was 0 decimal point, 10 zeros, and then a 667. This sucker's 9 billion basically. And it has the units of newtons meters squared per coulomb squared. I should say that we could also write this the other way, which is the way I generally prefer to write it, as Q1 Q2 over 4 pi epsilon naught r squared, where epsilon naught is called the permittivity of free space, and that is about 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. So that's the way I normally like to write it. But you can see it's got problems by writing it that way. I've got to write not only a constant like a K, which is a pain in the butt enough, but I've got to write a constant epsilon zero. Epsilon's harder to write than K, and it has a subscript, so that means it's more trouble. And it has a pi, and it has a 4. So it's a lot more writing, but in the end, Maxwell's equations are all in terms of the permittivity parameter, not this K. This K is just called the Coulomb's constant, whereas this epsilon zero turns out to be something important, and it's called the permittivity of free space. So I'm not writing that down. You guys can get that from your reading, but the main thing is that you just need to know that these are the two versions. So one of the things that you can do for extra credit is you can calculate the attraction between the proton and the electron in a basic hydrogen atom. Remember, basic hydrogen, not deuterium, not tritium, has one proton and one electron, and that's it. And the electron basically has an average distance between it and the proton that's equal to the Bohr radius, which is about 0.529 times 10 to the negative 10th meters. So if you go ahead and calculate the gravitational attraction between the proton and the electron in a hydrogen atom, and then if you go ahead and calculate the electrical attraction between the proton and the electron in a hydrogen atom, and then you calculate the ratio of the two, specifically calculate the Coulomb force divided by the gravitational force, you'll get a really large number that tells you how much stronger the force of gravity, or excuse me, how much stronger the force of electricity is than gravity. Okay, so that's an extra credit that you can do. It'll be at the bottom of this week's module in the extra credit section for you guys to work on. You will have to look up, of course, if you don't remember them off the top of your head, you'll have to look up the charge of the electron, which I have written right here, the charge of the proton, which I have written right here, and the Bohr radius, which I did mention was 0.529 times 10 to the negative 10th meters. So y'all can check that out as well. I will tell you that when you use this equation, you do not, or at least I do not advise, because it's a pain in the butt and there's no real good reason to do it, but you never put in the charges sign into the Q1 or Q2. You just each time you examine two particles that are affecting each other, or a big thing of charge and one particle that's affecting each other via Coulomb's law, you put the magnitudes of the charges in for Q1 and Q2. You never put minus or a negative sign in for Q1 or a positive sign. They're always going to be positive, of course, but you never take the time to actually put a sign in there when you're using it. Okay. What you do is, again, you notice, oh, these two charges are the same. They're both positive, or they're both negative. Therefore, they're going to repel. Or these two charges are unlike, one's positive and one negative. That means they're going to attract each other. And that's what you use to decide the actual direction of the force. And I'll tell you that just like the law of gravity, Coulomb's law of electrostatics gives us a very prescriptive method of figuring out the direction of the force. In the case of Coulomb or of Newton's law of gravity, you had to imagine M1 and M2 were point particles, and then you draw a line that connects the point particle M1 to the point particle M2, and the force of attraction between M1 and M2 would be along that line connecting M1 and M2. Now, if M1 and M2 were not particles, then you would take and draw a line from the center of mass of M1 to the center of mass of M2, and the force of attraction would be along that line as well. Well, the same thing's true in Coulomb's law. If you're dealing with particles, then you imagine a line going from the point particle Q1 to the point particle Q2. And then, depending on whether the signs were alike or the signs were different, you'd either get an attractive force or a repulsive force. But in either case, that attractive or repulsive force would act parallel to that line that connected the two point particles. And again, if you weren't dealing with point particles, you'd go from the center of charge of Q1 to the center of charge of Q2, draw a line, and then the force would act parallel to that line, whether it be attractive or repulsive. So, anybody have any questions on that? All right, I will tell you that we're basically, because I'm skipping the a lot of the conceptual stuff, which again I love that stuff, and I recommend you go look at my friend Kevin Mitchell's YouTube channel as well. He's got a lot of fun videos he's made up there. I usually do them in class, but we don't even really have much time to do that in the calculus-based physics class. But the first few sections are basically what I'm telling you guys you need to read and understand thoroughly, even though I'm not going through it at every little bit. But it's 21.1 static electricity, electric charge and its conservation, 21.2 electric charge in the atom, 21.3 insulators and conductors, 21.4 induced charge, the electroscope, so you should know what an electroscope is. And then finally 21.5 we get to Coulomb's law, which is where I'm starting right now. Okay. So now that we've gotten to Coulomb's law, I want to go ahead and remind you that like charges repel and unlike charges attract. And I want to work a specific problem for you just to give you an idea of how you go about doing these. Example 21.1 is really rudimentary, but that gets you started off on the extra credit that I told you, because that's basically doing the exact same thing. You're calculating the force of attraction between the proton and neutron in a hydrogen atom. That's a little simpler than I really wanted to do for my first example, so I'm going to try another example. And 21.2 is also a little too simple. I'm going to leave that one to you guys. But let's look at 21.3. I do like that. So example 21.3, three charges in a line. It says three charged particles are arranged in a line as shown in figure 2118A. Calculate the net electrostatic force on particle 3 due to the other two charges. So again, these are forces, and forces behave like vector quantities. So if you have multiple things acting, causing a force on one thing, they just add like vectors. So in this case, I'm going to go ahead and write the example. The example is 21-3 or 21.3 is the way I like to write it. And what I have here is a charge of negative Q1 is negative 8.0 microcoulombs. And this coulomb, by the way, is a huge unit of charge. To give you some idea, a lightning strike basically carries a butt ton of charge from a cloud maybe to a person or a tree or something that it strikes. And one lightning strike is it's not unreasonable to get maybe 100 to 1,000 coulombs of charge carried by a lightning strike. So that gives you an idea that wow, a coulomb really is a butt ton of charge. But anyways, here's the leftmost particle, Q1, and then a little ways down, there's a positive particle, and that one is Q2. and that one has a charge of positive 3.0 microcoulombs. And then a little further along, there is yet another negative charge, and this one is Q3, and its charge is negative 4.0 microcoulombs. Okay. And they ask us to calculate the net electrostatic force on particle 3. So what they want is F3 equals question mark. Now that is a vector quantity, so I want to put it that way. I will tell you that this distance from here to here is 0.30 meters, and this distance from here to here is 0.20 meters. So that's the distances, and we're sort of imagining them as if they're lying along the positive x-axis, and we might say the positive y-axis is here, so that Q1's technically at the origin. Q2 is 30 centimeters to the right of the origin, and Q3 is 50 centimeters to the right of the origin, and we want F3. So, solution for the solution, we want to use Coulomb's law, which says that F is equal to Q1 Q2 over 4 pi epsilon naught R 1 2 squared. Now I just put that in there to remind us that R 1 2 is, or to put the subscript 1 2 on there to remind you that R in this case is supposed to be the difference between Q1 and Q2, the distance between them. I think I said difference by accident. Now the other thing we need to know is that F3, the force that we're trying to calculate, is supposed to be the force on particle 3 due to particle 1 plus the force on particle 3 due to particle 2. Now, you might also say, what about the force on particle 3 due to particle 3? Well, particle 3 can't apply force to itself. Okay? So that's the big trick. Now, what we're going to do is we're going to use our knowledge of like charges repelling and unlike charges attracting to decide what directions the forces are going to apply, point, and we're going to use the formula to calculate the magnitudes of them. So let me start off by calculating F31. So F31 is supposed to be the force on particle 3 due to particle 1. Well, particle 1 is a negative 8.0 microcoulomb charge, and particle Q3 is a negative 4.0 microcoulomb charge. So that means they are like charges, and like charges repel. So if I'm talking about the force on particle 3, what I'm saying is particle 3 is going to be pushed to the right as a result of the force that Q1's giving it. So that's all I have to do. The line between them is clearly just the x-axis, so I know the force is going to be horizontal, and the fact that they're repulsive tells me that Q3 is going to try to be pushed away from Q1. That means F31 is going to point to the right. The magnitude of that, I'm going to use the K version instead of the 4 pi epsilon naught version, but the magnitude of that is 8.988 times 10 to the ninth Newton meters squared per Coulomb squared. And I don't always put the units in, but I try to do it the first time I use any equation just so you'd see what happens. So in this case, I'm going to take F3, which is 4.0 times 10 to the negative 6 coulombs. Notice it was negative, but I didn't put that charge in. I'm going to treat all the charges as if they're positive. The same thing with Q1, which is negative 8.0 microcoulombs. So I'm just going to write 8.0 times 10 to the negative 6 coulombs. And hopefully y'all all remember that that's because micro means 10 to the negative 6. It's 1/1,000,000th. So that's K times Q1, Q2. Now I've got to divide all this by R squared. Now the difference distance between Q1 and Q3 is 0.50 meters, so I'm going to write 0.50 meters and then square all that, you can see that when I square this 0.50, that unit of meters squared is going to cancel out with these meters squared here. You can also see that these coulombs are going to cancel out with the exponent of 2 down there and get rid of the entirety of the coulombs. So all I get out is a Newton, and that's what we wanted. And I'm just going to put plus here to point out that it points to the right. Okay, so that's why I wrote the positive symbol there. Now 8.988 times 10 to the ninth times 4 times 10 to the negative 6 times 8 times 10 to the negative 6. All of that gives me 0.287616, but now I got to divide it by zero point 0.5 squared. So I divide by parentheses zero point 0.5 squared, close parentheses, and I get 1.150, carrying two extra digits beyond sig figs. So this is 1.150 newtons to the right. Okay. Now I've got to calculate F32, and F32 is going to be 8.988 times 10 to the ninth. I'll leave the units off this time. Now 3 still has a charge of 4.0 times 10 to the negative 6. Notice I can't put in micros in there, okay? If there was just one, I could do it and then it'd come out in micro newtons for the units, but in general, we just don't do that. We go ahead and bring everything to the base unit. Now, charge 2 is actually a positive charge, and its charge is 3 microcoulombs. So I'm going to write positive 3 times 10 to the negative 6. Notice I'm only using positive charges uh, for Q1 and Q2. Now, the distance between particle 3 and particle 2 is, I got the negative 4, I got the 3. Okay. The distance between them is 0.20, and I'm going to square that, of course. So now I do 8.988 times 10 to the ninth times 4 times 10 to the negative 6 times 3 times 10 to the negative 6. That gives me 0.107856. Now I'm going to divide that by zero point 0.2 squared, parenthesis zero point 0.2 squared, close parenthesis, and that gives me 2.696 newtons. Now, this one, the positive and negative particles are actually attractive because the Q2 is positive and the Q3 is negative. So this one's actually pointing in the negative direction. So I'll put that there, and that just means to the left. Okay, so what I have is a force of 1.150 pointing to the right, and then a bigger force of 0.269 pointing to the left. And since they point in opposite directions, we're actually, even though technically we're adding, because one of them points to the left and the other one points to the right, we're basically subtracting. Okay, so I can now say that the magnitude of F3 uh, is equal to the magnitude of F3. Let's do the bigger one first. So I'm going to do F32. Actually, I'm going to do F31 plus F32. And the fact that they're negative will take care of all that. And it'll come out to be negative, and that'll just tell me, oh, this force is to the left because it's negative. If it came out positive, it would have been this force is to the right. So now I'm going to take the, oh, no. Oh, okay, I see what I did. So I'm going to say 1.150 plus negative 2.696. And that gives me negative 1.546 newtons. So the net force, F3, is actually equal to 1.546 newtons. And what I'll say is I'll say that's in the negative I hat direction, and that specifies to us that given the diagram, it's pointing to the left and is parallel to the x-axis. Anybody have any questions on that? All right. So that's a typical type of problem we want to work. Another one we want to work is being able to figure out what if you have a bunch of different forces that aren't all acting along one line. Then you have to do something that's two or even three dimensional. So that's going to bring us to example 21.4. And example 21.4 says calculate the net electrostatic force on charge Q3 shown in figure 2119A due to the charges Q1 and Q2. So what we have here is Q1 and Q2 along the x-axis and then Q3 up along the y-axis. And what we're wanting to do is calculate the net force on Q3 due to Q2 and Q1. So to do that, I first want to draw a coordinate system so that I can list all this stuff and put it exactly where it's supposed to be. So there's my y-axis, and there's my x-axis. Okay. Now, what I'm going to do is I'm going to put a charge right here, and that is Q2. And this charge is Q2 is equal to positive 50 microcoulomb. And I'm going to go on the assumption that that's 2 sig figs. Also, over here, I'm going to put a charge Q1, let's say right about here. And this charge is Q1, and that one has a charge of negative 86 microcoulomb. That one obviously has 2 sig figs, so we're good on that. And I also know that the distance between these along the x-axis is in fact 52 centimeters. Now, if I go 30 centimeters upward, then I'll run into particle Q3, which is also red, and I'm going to put it right here. And this one is Q3, and it has a charge of positive 65 microcoulombs. Now, your book has been nice enough to give us some data. For instance, it tells us that this right here is a 90-degree angle. It also tells us that this distance right here is 60 centimeters. Again, I'm assuming everything has 2 sig figs at least. And it tells me that this angle right here is 30 degrees. Now, as I said, what we're asked to solve for here is F3 equals question mark. As far as the solution goes, I'm going to say solution F is equal to K Q1 Q2 over R squared, and F3 is going to be equal to the force on 3 due to particle 1 plus the force on 3 due to particle 2. So we're going to have to compute all that, but we'll start off by just calculating the magnitudes because that's what Coulomb's formula allows us to easily do. So I'll first compute those magnitudes and then try to draw on the diagram exactly what those vectors look like. So let's start off with F31. F31 has 8.988 times 10 to the ninth times, and this is 3 and 1, so 3 has 65 times 10 to the negative 6, and the other one has 50 times 10 to the negative 6, and then all of that's going to be divided by 0.30, and that's going to be squared. So when I do this computation, you guys should hopefully be backing me up here in case I make any careless mistakes. Y'all will catch them. So I'm doing 8.988 times 10 to the ninth times 65 times 10 to the negative 6. Oops. Times 10 to the negative 6 times 50 times 10 to the negative 6. That gives me 29.211 for the numerator. Now I'm going to divide that by parentheses zero point 0.3 squared, close parentheses, and that gives me a force of 324.6 newtons. Now, we only really had two sig figs, so the 4 and the 6 aren't sig figs, but we at least know the magnitude. Now, F31, we have to figure out, is that a repulsive force or is it attractive force? And then once we figure out it's attractive or repulsive, we got to figure out what direction does that point. And this is where the physics of this comes in. The rest is pretty much just math, and that's fairly trivial. But if you want to know the physics, you got to be able to figure out this stuff. So first off, Q2 and or excuse me, Q1 and Q3. Ooh, wait a second. I just realized I took the data for one. I meant to calculate F31, but I calculated F32. So it's okay because I'll just change this number here, but we're going to change this to 2. With that in mind, now I've got 50 and 65. Okay, that's what I actually intended to calculate, but I evidently wrote it down as 3-1, but it's technically 3-2. So again, everybody make sure y'all made that change from F31 to F32 because I'd sort of started it doing it one way and evidently changed the number just by not paying attention or what. I'm not sure. But the main thing is the number should come out right. We see that the two charges are positive. So does that mean the force is repulsive or attractive? Exactly. They're like charges, so they're repulsive. So now we're talking about the force on three. Does that mean the force on three points up, points down, points to the left, points to the right, points up and to the left, points up and to the right, points down and to the left, points down and to the right? Which direction does F31 point? It is repulsive. Remember that. So that means it's like charge Q3, which is the force we're calculating on. Okay. So what we want to do is figure out what does 3 look like it's going to do. Well, if you were standing next to a stinky person, you would obviously want to run away from said stinky person. That's what repulsive means. So in fact, you expect Q3, if it had its ability to move however it wanted, it would actually run away from Q2, and that would be pointing up. So it points upward. Now that means we could just call the force 324.6 J hat. That would be perfectly fine. But right now, all I cared about was this. So I'm going to go ahead and write this force as right here, and that's F32 points upward. Everybody see the little vector that I drew? Okay. Now that is parallel to the line that connects Q2 and Q3 together, which is the way we're supposed to figure out the direction of this, just like we did with Newton's law. Now I'm going to do F31. This time I'm going to try to do actual F31 instead of F32 by mistake. So F31 is going to be 8.988 times 10 to the ninth, again, leaving off the units. Now 3 still has a charge of 65 times 10 to the negative 6 coulombs. But the other particle is negatively charged, and it has a charge of 86 times 10 to the negative 6 coulombs. And the distance between those two particles is in fact 60 centimeters. So I'm going to divide all that by 0.60 and square it. So let's calculate this quantity, 8.988 times 10 to the ninth times 65 times 10 to the negative 6 times 86 times 10 to the negative 6. Notice I did not put the negative sign in there. Everything's positive. Now, just doing the numerator, I got 50.243 for the numerator. Now I got to divide that by zero point 0.6 squared, parentheses, zero point 0.6 squared, close parentheses. And this gives me a force of 139.6 newtons. Now, in this case, the two forces or the two particles have a charge of negative 86 microcoulombs and a charge of positive 65 microcoulombs. So, are these repulsive or is this force attractive? Yes, these two are attractive because they're unlike charges. And in this case, that means this force actually points down and to the right, and it points right along that dashed line that I have. So what I'm going to do is draw this force right here. Now that force is actually markedly smaller than the F32, but I'd already drawn the F32 and I can't make it any bigger. And if I made this one even smaller, I don't think you'd see it. So I'm just going to leave this as the force F31 pointing that way. Okay. Now, what we need to do is break F31 into components. Now, the X component is, of course, positive, and it'd be right here for F31, but the Y component is actually negative, so it'd be right there. If you remember, of course, this is 30 degrees though. So I'm going to take the time to write down what the sine of 30 is and what the cosine of 30 is, and then use that to solve for the X component of F31 and the Y component of F31. So looking at F31, we get, I'll go back to blue. I don't know why I'm writing in red. Sine of 30 degrees is equal to opposite over hypotenuse. The opposite is, of course, in this case, it's the y component. So I'm going to say F31y over the hypotenuse, which is really F31. So that's the 139.6 newtons. And again, that one only had two sig figs as well. So I'll put it like that. And then we can say, obviously, F31y, because it's negative, I'm going to go ahead and put this negative sign there, or this negative sign there. And I'm saying sign, S-I-G-N, not S-I-N-E. So 139.6 times sine 30 gives me 69.8, so that's negative 69.80 newtons is F31y. Now cosine 30 degrees, remember some old horse is sine equals opposite over hypotenuse. Ka or Kama hopping is cosine equals adjacent over hypotenuse. So in this case, it's going to be F31 x over the hypotenuse, which is 139.6 newtons. And this one's actually positive, so I'm going to say F31x is equal to positive 139.6 times cosine 30. And in this case, I get 120.9 newtons. And again, two of those digits are not sig figs, so I underlined them. So now what I have is F3 is equal to F31 plus F32. And F31, that was the one we just finished calculating. So I'm going to write that as 120.9 newtons. And that is in the x direction. So I'm going to write it as an I hat. Excuse me. Sorry about that, everybody. Now, the y component of that, of course, is negative. So I'm going to say plus negative 69.80 newtons, and that's in the j hat direction. And since it's negative, that makes it in a negative j hat direction. And now all I have to do is add 3,2 to it, and we already found out that 3,2 had a magnitude of 324.6. So I'm going to say plus 324.6 newtons. And that one actually pointed in a positive y direction, so that's just going to be a j hat as well. So this is a way we could do it. Of course, you could have just made a table and added the x components and add the y components and then get a new x and new y component. Either way, this is acceptable or that way is acceptable. It turns out that the only thing that has any x in it is the F31, so that's going to stay the same, 120.9 newtons I hat is the x component of the resultant vector. Now the 324.6 minus 69.80 gives me 255, or excuse me, 254.8. And notice that came out positive, and that's the j hat direction. So the y component of the F31 was quite a bit smaller than the y component of F32, so that's why it won. So our net result is the sum of these two, and we can actually write it. If you looked up here, if I'd actually drawn this picture here to scale, it would be a little easier, but it's not to scale. It would more like be a scale if I did like this to that. And then the force would be right here. That's roughly where it's going to be because this guy is a little bit bigger than a third of the length of this guy. So that's why I had to correct and put it way back here. But that's basically where it is. I'm going to show you how to do this this way though. So what we have is a x and a y. There's my x. There's my y. I know my y component is 120. So I'm going to say this one is 120.9. And the x component, I actually
Oh,
need to,
Mr. Younger,
yes,
I can't, or we can't see the graph that you're drawing on the bottom. We can only see the top portion of the
about
graph.
now. Uh,
No. I mean, it was moved a little bit, but it reverted back to its original dimensions.
okay, do you see this itty bitty thing right? Because I'm seeing it on my side. That's what's confusing me. You see this down here?
Barely. I'm
Okay.
not, oh,
Maybe it's your screen because I'm seeing it on mine. Yeah, I
I,
think it's something on your screen. You might need to adjust the zoom or whatever.
oh, okay.
You got it?
It's the bar. Never mind.
Oh, okay,
My bad.
gotcha. No problem. I appreciate you letting me know. That's I definitely just screw up that way, so it's certainly helpful. So this was 120. The other one's 254. That's almost twice as big. So to draw it to scale, I really want to try to make it more than two of these. I want to try to make it like four squares over, like that. And this one, of course, is 254.8. Okay, so that's the two vectors, and I've got them drawn in a tail-to-tail fashion. So we know that the result will be coming from completing the parallelogram, which will be this guy. And I need to find out what that angle is and what that magnitude is. So the magnitude of F3 is just given by the Pythagorean theorem. I'm going to take 120.9, I'm going to square that, and basically, because I only had two sig figs, that means only the ones, tens, hundreds, only the thousands and 10,000s are sig figs there. Now I'm taking the 254.8 and I'm going to square that. And that also tells me the thousands and the 10,000s are all that's significant. I have to do that separately to figure out what the sig figs will be. So I'm just trying to be careful. So this ends up giving me the square root of 79,540 newtons squared. And these are the those are the actual digits that I got. So now I'm going to take the square root of that. Everybody see what those are? I'm getting ready to erase it, but I just wanted to give you those digits for a brief second. So I'm now going to take the square root of this by raising it to the zero point 0.5 power. And that gives me 282.0. So the magnitude of this is 282.0, but we know it only had two sig figs, so it's 2. So that's the magnitude. And I'm going to say at, and the phi is going to be given by phi is equal to the tangent inverse of 120.9 over 254.8, like that. So I'll take shift tangent inverse parentheses 120.9 divided by 254.8 close parentheses, and this gives me an angle of 25.4 degrees. Actually, I'll write it as 25.38 degrees. So I've carried two extra sig figs as that as well. Anybody have any questions on that? Now looking at this, they called it 280, which is the same thing I got for theirs, my magnitude, and they found the angle, though they were measuring a different angle than I did, they found the angle to be 65, which obviously is the complement to the 25 that I got. So, that's the difference. They actually measured this angle, whereas I measured this angle. But that's it. Anybody have any questions on how that was done? All right. Now there is I would like to go ahead and work all the different examples in here, and there's a lot of good reasons for it. Like the next example, it says make the force on Q3 0. So it says in figure 2119, where could you place a fourth charge Q4 equals negative 50 microcoulombs so that the net force on Q3 would be 0? What you have to do with that particular problem is you have to calculate the total force that's already there as a result of Q3 and as a result of Q3 and whatever else is there. Actually, let me see. Where could you place a fourth charge? Oh, okay, I see. They're referring back to the previous problem. That's why I wasn't getting. I'm like, I don't see any charges here. So what you want to do is now that we have a force, this F3 that we just found, where could we put a force to cancel that? Well, this force points up and to the right. So if we put a positive particle there, which is what Q3 is a positive particle, that positive particle would feel a force of 282 newtons pointing up and to the right at an angle of 25 degrees roughly. But if we made another force pointing exactly the opposite way and gave it the exact same magnitude, then we would cancel the force out and make it 0. So that's all we have to do. We have to take the line that connects Q3, which is this spot right here, okay? And we imagine a line, and remember, this is the 25 degrees that we just found for the final vector, so it should be something like that. What we're going to do is take along that line and put a Q4 right here, and if since it's negative, it would actually attract this positive particle to go that way. That's not what we want. We want that positive particle to point the other way. So we would actually want to take the Q3 or the Q4 and put it over here. Then it would be attractive to go this way and it would cancel it out. All you'd have to do is take 8.988 times 10 to the ninth, that's the K, times 65 times 10 to the negative 6, that's the Q3, times 50 times 10 to the negative 6, that's the Q4, and set all that equal to, again, putting finding a distance, but setting that equal to 282.0 newtons and solve for the distance, and it would tell us that we'd have to put the Q over here some distance away, and by doing that, that would cancel out the force. So that's actually what's happening in the next example. But I want to move on and show you how we make Coulomb's force a force that's not action at a distance. So I told you guys when we covered Newton's law of gravity that Newton had a problem with it. For instance, he knew that there was no reason that he could understand as to why or how an object like the sun could reach out across space without physically touching the earth and pull on it. That was what we called action at a distance. So the way that you can address that is you could imagine that one of the masses, like in the case of gravity, the sun creates a field around itself, and then any other mass coming in there will feel a force by just multiplying the mass of that new particle times the existing field strength as a result of the sun, and that would give you the magnitude, and of course the direction would just be pointing towards the center of the sun. Well, we can sort of do the same thing here with the electric field in that we can imagine an electric field as obviously something that results in a force like we had for Newton for Coulomb's law of electrostatic force, but let's imagine one of them as creating the field and the other one is feeling the force. To do that, we do the following. So I'm going to take my formula, which is F is equal to, and it's convenient to use K here, so I'll use K just to make life a little easier. That's K times Q1, and actually let's put them on a slightly different footing. I'm going to call one Q because I'm going to picture that big Q as the source of the field. And then I'm going to call the other one little q as the charge that is going to be felt, or that's going to feel the force, if you will. So what I'm imagining is big Q is the thing that's creating the field, and little q is the thing that feels the field. Now, I'm going to introduce something called the electric field, E. Now, I can write vector symbols over here, but I haven't given you enough stuff to call this a vector. I'd have to actually put vectors on it to put a vector on the left-hand side. The right-hand side has to be a vector. And I haven't given you the tools to figure out what vectors to put it. So I'm keeping it all scalar right now. But what I'm going to imagine is I'm going to take the force that we just calculated, which was K, Q, Q over R squared. That's the force. Okay. Now I'm going to imagine dividing this force by the thing that's feeling the charge. So I'm going to divide it by Q. And then that would make the actual, what I call the electric field. But in doing that, there's a little bit of a problem because if I imagine a charge big Q as altering the field around the charge big Q, then there's no reason to assume that the charge little q is not going to do the same thing. So to get out of that conundrum, we're going to imagine taking ever smaller and smaller little q's until it asymptotically sort of approaches a fixed value. of the strength of this electric field. So instead of this, I'm going to say E, the electric field, is equal to the limit as Q approaches zero of F over Q. Now, at this point, I can write this as a vector and I can write this as a vector, and then both is actually an accurate vector equation. So this is our definition of the electric field, and I want you to think of that limiting process as just a way to make sure that the q, the lowercase q, is not so big that it alters the field that we're using to calculate the field due to big Q. Okay, so that's why that's so. In practice, the equation's just going to be that F is equal to Q times E. That's how we're going to use the equation in practice. And when I say in practice, I mean if we needed to calculate the force from the electric field, or if we needed to calculate the electric field from the force, then we'll just use F is equal to Q times Z and solve it that way. We don't have to think about that limiting process. That limiting process was something we had to do to make sure that we weren't incorrectly ignoring the effects that little q will have on the field created by big Q. Okay? So that's how we're going to define our electric field. And the units of the electric field, of course, you can see they're equal to the units of the force divided by the units of the charge. And that, of course, is a Newton per Coulomb. Later on, we'll learn that that's exactly the same thing as a voltmeter, a volt per meter, excuse me, and that'll be nicer way of dealing with it. But right now, we're going to think of the electric field as having a unit of newtons per coulomb. Okay, so if you wanted to think about that, we could say, well, what is the electric field at Q3 from example 21.4? Well, we already calculated what that force was. We found the force was 282.0 newtons. So F3 was equal to 282.0 newtons at 25.38 degrees. And that was measured counterclockwise from the positive x-axis. And now I can put a vector symbol over F3. So that's F3. If I want to know what the electric field is at Q3, then I need to take the force at Q3, which is this F3, and divide it by the charge of Q3. So E at Q3 is equal to F3 divided by Q3. So this is what I meant when I said in practice we're just going to use F equals Q times E, or in this case E equals F over Q. We're just going to do it like this. So I'm going to take F3, which has a magnitude of 282.0 newtons, and I'm going to divide it by the magnitude of Q3, which we recall was 65 microcoulombs. So I will say 65 times 10 to the negative 6 coulombs. And now I'm going to say 282 divided by 65 times 10 to the negative 6 gives me 4.338 times 10 to the sixth newtons per coulomb. So that's the magnitude of the electric field. And therefore, the electric field E3 would be 4.338 times 10. Oh, I should go ahead and, yeah, times 10 to the sixth newtons per coulomb at 25.38 degrees. Now, notice if I had actually, if Q3 was actually a negative charge, this is a case where I'd actually need to think about dividing by that negative. Uh, Mainly just to remind me, oh, okay, since I'm going to do this, the electric field will point in the opposite direction as the force. So in this case, I'd add 180 degrees to that if the Q3 had been negative, but in this case, the Q3 was positive. So this is perfectly acceptable. So that's how we're going to deal with it now. We're probably going to very rarely use the force equation. We're actually going to tend to use the electric field equation. So, in terms of that, Coulomb's law for the electric field is E is equal to uh, Q over 4 pi epsilon naught r squared, which is also equal to K Q over r squared. So that's a new equation that we can use now because notice all I had to do was divide out the charge that we're saying feels the force. Okay. So for another extra credit, guys, I would like you to go ahead and try using this idea, specifically the idea that E3 is equal to E3 1 plus E3 2, like that, compute the electric field, find the magnitude and direction, and then calculate the force and see if you get the same equation or get the same result. Oops. So there's an extra credit for you guys if you want to do it. Again, don't have to, but that would be some good practice. When we start next time, I'm going to jump right into using a vectorial form of this electric field equation where it actually computes a vector, and then I'm going to do some really, really rigorous calculus calculations to derive, for instance, the electric field due to an infinitely long string of charges. Also, for calculating the electric field over a infinitely large plate of charge, and calculate the electric field due to a sphere of charge, that sort of thing. Actually, I'm going to do a loop, a little hoop of charge, if you will, like a hula hoop. Okay, that's it. You guys are free to go. Give me a holler if you need anything, and don't forget to chat me your first and last name if you haven't done so already. But you're free to go, and thank you for coming. I saw you just got back in, Alex. Everything okay?
Yeah, apparently touching the earbuds exits out of Zoom. I didn't know that.
Yeah, I had some earbuds do some weird things for me like that. I don't realize you just touch them every now and then, it like everything turns off or it changes to a new app. So that's fun. Anybody else have any questions? I've now got two Alexes in my class.
Yes, and we both would want to ask a question.
Yeah, what's up,
Um,
Alex?
so I wanted to ask about the relationship between force and the electric field.
Hmm.
With force, I feel like it's a vector. In a vector field, it's kind of linear because it points in a direction.
Hmm.
But in the electric field, wouldn't that point in all directions in a way?
It's sort of like like I left you without a description of what the direction of the electric field is. So what you now do when you calculate an electric field, you calculate electric field at a particular point.
Hmm.
And you imagine when you want to try to figure out what direction the electric field is, you imagine putting a positive test charge at that point, and you say, okay, if I stuck a positive test charge at that point, which direction would the force point? That's the direction of the electric field. So that's the way that's going to deal with it. But you're absolutely right to notice that it's almost like I didn't give you enough information to figure out the electric field. So in the case of E3 that we just calculated, I've calculated the magnitude was what 4.3 times 10 to the 6 newtons per coulomb, and that's specifically at the location where Q3 was. So basically, what you would do is you'd say, okay, if I want to calculate the electric field there, I'm going to imagine a positive particle being right there, and then I'm going to see which way the force would feel compelled to move, or which way the positive particle would feel compelled to move. In the case of the charge Q3, that is a positive charge, so it's going to feel exactly the same way as the positive charge force was. So it's going to point up and to the right. Therefore, I was able to just write 25.38 degrees because that's the same direction the force had. Does that make sense?
I believe so. Yeah, I'll definitely out a problem and see it.
Hmm.
But would
Just
that then
remember
mean,
the
Mhm.
equation, just in case you're a little confused as to the electric field. What I want you to think about is this equation up here in the top left. This one. You can think of it as I've got to have a Q and a Q to make a force.
All right.
In order for me to get that force, I got to take K, I got to multiply that by Q, and then multiply that by the other Q, and then divide all that by R squared. Why not just save this Q for later? In which case, the K times the Q over R squared is what I call the electric field. And if I ever need to calculate the force, I just multiply it by Q.
Oh, okay. I see.
Does that make sense? That's really all it is. We're just trying to say, hey, I want to stop one step short of calculating the force, and I'm going to do that by leaving out one of the charges. Specifically, I'm treating one charge as the source of the electric field and the other charge as the thing feeling the electric field.
Okay. Yeah, that definitely clears a lot of things up then.
All right. Well, I hope that helped.
There it does. Cool.
All
Thank
right.
you so much.
No problem. Have a good one, Alex. Let me know if there's anything else I can do for you.
Will
I
do.
did move. Y'all do have a test this Friday or this Sunday, so make sure y'all get that knocked out. It's an online test. But
Right.
other than that, I'll see you later.
All right. Adios, amigo.
All right, see you, bud. Bye, everybody.